So let's actually go to advection equation and go through a very similar procedure to figure out how, first of all, how to approximate it with finite difference, and how much error are we committing, and how stable our equation is. And here we're going to be saying that how what we have learned is going to carry over here, but also, I mean, the method is going to be very similar. So that's going to show you how general the method is, but the conclusion is going to be different. It also shows kind of what we have learned, what kind of different results can we produce using the same method. Okay, so advection equation is, it's a little bit too thick. For advection equation, what we have is partial w, partial t plus a big U, partial w, partial x is equal to 0. All right, and we know analytically the solution advects in spatial domains. Wxt is equal to w0 of x minus big ut, right? So that's our analytical solution, not numerical solution. So numerically, we first aim to perform a semi-discretization of this equation. And in order to do that, we want to approximate the first order spatial derivative. And anybody wants to suggest how do we approximate the first order derivative of a function? What is a first order derivative? If, we can use forward order. But can somebody tell me what is if the second order derivative is the curvature, what is the first order derivative? It's just the slope, right? So we have the ith grid point I delta x of a function. It's just the slope over here. And if I know the two neighbors, we can basically use, as you suggested, the forward Euler or backwards Euler, right? If I use forward Euler, I would take the slope over here. If I use backward Euler, I would take the slope over here. Okay? The question is what to use. Unlike in discretizing the time derivative, there is actually no obvious difference between if I use forward or backward Euler, right? In time derivative, if I use forward Euler, the equation, the solution procedure becomes explicit. It's easier to implement because the time has a direction, has a directionality. Here in space, it's not obvious which side we should use. So let's just pick a side. All right. So let's just do as you suggested, the forward. Yes.
Does anyone take both and take an average forward?
Yeah, you can also take both and take an average. So that's a third possibility, right? So let's analyze all of them. So okay, so we have three competing approaches suggested over here. The first approach is forward Euler plus u wi plus 1 minus wi divided by delta x is equal to 0. Second approach, backward Euler, wi minus wi minus 1 divided by delta x equal to 0. And the third approach is, let's say, if we take an average between them, which is wi cancels, right? Wi plus 1 minus wi minus 1, and take an average, I would have 2 delta x equal to 0, right? We can call this forward. This is backward, and this is let's call it central because it's average between left and right. All right. Okay. So all of these schemes looks good. So we already solved the first problem, how to approximate a derivative with arithmetic. It seems to be even easier in this case. So how much error do all of these approximations make? What tool do we use? Taylor series, yes. So let's also analyze all of these cases using Taylor series. So all of these cases actually involve the three numbers, right? Wi plus 1, Wi minus 1, and Wi. We use the same Taylor series expansion, and we can figure out all of these three by just expanding these 3 points. So Wi equal to Wi. Wi plus 1 equal to Wi. I'm just going to write it. We should be already familiar with it. Wi prime, first derivative, plus delta x squared over 2 Wi double prime. Okay. Plus etc. So Wi minus 1 is equal to Wi minus delta x Wi prime plus delta x squared over 2 Wi double prime plus etc. Right? So we should already be familiar with Taylor series by now, I hope. Okay, so that's the Taylor series. And let's analyze the error one by one. The first case, we have forward difference. Okay. And for an error analysis, we want to look at the difference between this, right? Which is actually Wi prime. That's what we wrote. Yeah, I'm just going to write Wi prime. Okay, it's going to be equal to, we plug in the numbers. The first term cancels. The second term, the delta x cancels with the delta x. So what we have is Wi prime, okay, plus this minus Wi prime. Agreed? Okay, so the first term comes from the first order term in the expansion of Wi plus 1, right? And the second term comes from the second order term. So this cancels out. What we get is half of delta x times Wi double prime. Okay, somebody tell me what order scheme is this? It's first order scheme because the approximation error is proportional to delta x, as opposed to in the previous case is proportional to delta x squared. Right? Okay, so it's a first order scheme. Clear. And the error is proportional to the second order derivative. Similarly, we can do Taylor series expansion of this. Okay, we have now this minus this, so that minus delta x now becomes a positive delta x. It also cancels with this. We still get Wi prime. But the second one is we are having a minus of this, so we have a minus of delta x squared Wi double prime divided by this. So okay, we still are subtracting with the what we want to approximate. What we get is minus of this. Okay, clear? What order scheme is this? Still first order. Okay, so let's see if we by averaging this we get some better luck. So well, it's actually pretty obvious already from here, right? If we average this scheme and that scheme, this gets cancelled out. Okay, so we have actually the first order error actually is gone by just averaging these two. So that's a good suggestion. We have a higher than first order scheme. It also means that our Taylor series expansion is not enough because everything cancels. So let's add on top of our Taylor series expansion of another term, that is delta x cubed third derivative of I. And so we have minus here, third order derivative, triple prime. Okay, so now we can continue on our central scheme. I mean, actually, we can just take an average of these two truncation errors. And this term cancels out, so the double prime term cancels out. And what remains is actually these two adds together. So we have 2 times delta x cubed divided by 6 Wi triple prime divided by delta x. So that's going to be the leading error term. Oh, also divided by 2 delta x in this case. So the result is going to be delta x squared over 6 wi triple prime. So what order scheme is this? It's a second order scheme, right? So either left or right difference is going to give us a first order scheme, and central difference is going to give us a second order scheme. So that's application of the Taylor series analysis to figure out how much truncation error we have. Any questions?